In this video, we are going to discuss continuous distribution. This is our overview slide, which we'll spend less than 5 minutes on before we go over each of these two topics in more detail and with more examples. Our first topic is considering what happens as we move from histogram to continuous distributions. We look at these 4 histograms here, and this first one here, if you look at the bins, so this axis here, we're looking at heights. So the first category of heights we're looking at is the range between 140 to 150. The second category is 150 to 160. So each category represents 10 centimeters of height. We take a look at this next histogram where we further up divide each category by half. So instead of 10 centimeters, we only look at 5 centimeters. Here we have 140 to 145 centimeters, 145 to 50, 50 to 155, and then finally 150 to 160 over here. And you can see we end up kind of a more refined histogram. We can continue to make these categories smaller and smaller. In other words, each bin will represent a smaller number of centimeters, and you'll see then, instead of these blocks, after a while we start approaching this smooth curve as these blocks get smaller and smaller down to 1 centimeter or a fraction of a centimeter. We'll have a smooth curve, and that curve is our probability density function, also known as the density distribution, which leads to our second topic. A probability density function is any function that allows us to calculate probabilities, and the probability a random variable has a value between a and b. So for example, a then can be this 180, b can be right here where the blue line is. So the probability a random variable has a value in this block, the blue block, will be equal to the area under the density curve between A and B. So in other words, it's this shaded region here. If we have a full-on something like this here, where we have a curve, if we want to know the probability a variable is between this like 168 to 180, that's going to be represented by the area under the curve that I have shaded here. Now, because the density function represents probabilities, the areas under the curve will represent the probability. The curve is always positive because probability is always positive. So you'll never see a curve dip below this x-axis. And finally, the total area under the curve of a density function always equals 1. So in other words, when you've taken into account all possible cases, your probabilities will equal to 1. That concludes our overview. So now we'll come back and take a closer look at histograms to continuous distributions. The first thing we'll look at are these 4 histograms we had on our overview slide. They're histograms that represent the heights of U.S. adults. So how does changing the number of bins allow you to make different interpretations of the data? So in other words, the fact here that the bins are 5 centimeters wide? No, 10 centimeters wide, because it's 140 to 150, 150 to 160, 160 to 170, 170 to 180, 180 to 190, and then to 200. So each bin is 10 centimeters wide. Here, they're 5 centimeters wide because we're going from 140 to 145 to 150 to 155 to 160, 165, 170, 175, 180, etc. Here they're even smaller than 5 centimeters. My guess is they're 2.5, and here they're probably closer to 1. And the question is, how does changing the number of bins allow you to make different interpretations of the data? And the answer is more bins is going to allow you to make finer grain estimates. For example, consider the first 2 histograms, this histogram here and this histogram here. The first one where each bin represents 10 centimeters, and the second one where each bin represents 5 centimeters. And say we want to estimate the proportion of the population with heights between 160 and 165. Using this first histogram then, we would be looking at this bin, which goes from 160 to 170. So let me mark that we're actually going up to 170. Since we're interested in 160 to 165, which is halfway in this bin here, we can estimate that approximately half the people are between 160 and 165, and the other half is between 165 and 170. And I'll fill that in. That's our estimate between 160, 165. We'll say half of those people are between 160 and 165. This part of the bin, they're between 165 and 170. Now, if we look at the second histogram, you can see this first bin is 160 to 165, and then there's a bin between 165 and 170. And if you look at this, the bin between 165 and 170, it's higher than the bin between 160 and 165. So in other words, there are more people in this height range than in the height range of 165 to 170 than 160 to 165. So again, we see that more people fall into the 165 to 170 range than fall in the 160 to 165 range. We see that because the height of this histogram is taller. So if there are more people in this range, that means when we look at the entire range, 160 to 170, more of the people are in the taller range. So more than half of the people will be in the taller range, meaning that this over here, when we estimated 160 to 165, it's probably a little bit of an overestimate because this height range does not split up evenly. It splits up so that more people are in this green range, the 165 to 170. So that means our first histogram overestimated the percentage of the population between 165 to 170. That's not to say that this is bad data or that we shouldn't consider it. I mean, all of these are going to be an estimate, and when you sample, you're always estimating anyways. But it's just that the more bins you have, the finer grain, you can look at things at a smaller and smaller level and hone in on a small amount of population. In other words, you could hone in on people that are really very close to 160, maybe 159 to 161, in a way that here you'll be introducing more error. And then, of course, as you get into smaller and smaller bins, you'll have less and less error as you hone into your populations. We can do this quick example with this histogram here. You can see we go from 180 to 200, so halfway is 190. So this is 185. So each bin represents 2.5 centimeters here. Actually, it tells us that. So the shaded region represents individual heights between 180 and 185. We have some additional data. This blue shaded region represents 195,307 people. This green shaded region represents 156,239 people. And there's a total in this whole histogram 3 million people. So what proportion of the sample is between 180 centimeters and 185 centimeters tall? Well, that's going to be the 195,307 plus 156,239 divided by 3 million. It's approximately 11.72%. But the thing you want to take away from this video is it's going to be the area here represented or shaded in blue, and plus the area under the curve shaded in green. We have this one last question. We have 3 U.S. adults are randomly selected. The probability an individual adult selected is between 180 and 185 centimeters is 0.1157. In other words, approximately 11.57%. So what is the probability that all 3 randomly selected adults are between 180 and 185 centimeters tall? We are going to let P1 equals person 1 is between 180 and 105 centimeters tall. So P1 complement means they're not between 180 and 185. And then P2 is person 2 is between 180 and 185. Since the probability that one person is between 180 and 185 centimeters tall is independent of person 2 being 180 and 185 centimeters tall, we're going to use the multiplication rule for independent events. So the probability that P1 and P2 and P3 occurs is probability of P1 times probability of P2 times probability of P3. So that's equal to 0.1157 times 0.1157 times 0.1157, which is 0.115%. Remember, this is a percent, so it's like, what is it? Moving the decimal over 2 places. It's this is the decimal form of this percentage. It's very small. Our next question, what is the probability that none are between 180 and 185? So it's very similar because they're still independent events. So the probability that P1 complement and P2 complement and P3 complement occur is the probability of the three, probability of P1 complement times probability of P2 complement times probability of P3 complement. So we have 1 minus the 0.1157 times 1 minus 0.1157, 1 minus 0.1157 is approximately 69.2%. And you want to be careful that 1 minus part A, so 1 minus 0.115%, which is what we found is the probability all three are between 180 and 185, is 1 minus that is the probability not all three are between 180 and 185. But that means maybe 1 is between 180 and 185, or maybe 2 are between 180 and 85. So this probability here does not exclude the condition that maybe 1 or 2 are in this range. So if you want all three not to be between 180 and 185, that none of them are in there, you need to use this formula here. So again, my note is that this here, the 1 minus our previous answer, is a probability not all three are between 180 and 185, but 1 or 2 of the three may be in that height range. And that's a totally different answer to the probability that none are in the height range. What is the probability that a randomly selected person is exactly 180 centimeters tall? Assume you can measure perfectly. So that answer is 0. And it's sort of a theoretical answer because remember, we're calculating probability as the area between point A and B. If A is equal to B, then this is infinitesimal. The width of the thing is infinitesimally small, meaning there's not going to be any area because the area approaches, the width of the bin approaches 0, which means when you multiply for the area of the rectangle, you're going to multiply by 0, so you get a 0. And as I said, that's sort of a very theoretical way of answering that question. But that's the question, that's what the book is getting at. And the point is, so the thing you want to remember when we're talking about a continuous variable, a distribution, the probability of random takes one specific value, not a range, but one specific value is always going to be 0. Let's compare that to this question. Suppose a person's height is rounded to the nearest centimeter, so we can be, 0.1 off of the centimeter. Is there a chance that the random person is measured height will be 180 centimeters? And the answer is yes, because now if we're measuring to the nearest centimeter, we're looking for someone between 179.9 centimeters and 180.1 centimeter. And these we would round to 180. It might be also that they might also say, if we're rounding actually, it might be 179.5 to 180.5 centimeters. But the idea is as long as there's any width at all to the bin, then it's okay. We can find an area to the bin. It's only when the width of the bin is infinitesimally small, when you have a single point, that your probability is going to be equal to 0. To review what we covered, we talked about going from histogram to continuous distributions. We looked at histograms. Here we have bins that are separated by 10 centimeters each. And then we looked at what happened as we made the bins smaller and smaller. Here we had bins at 5 centimeters each, here 2.5 and something even smaller. And we saw that then our histograms start to look more and more like a continuous function. In other words, a smooth graph, a smooth curve. which led us to our next topic about probabilities from continuous distributions. And we call these probability density functions. So they serve the same purpose as histograms, but the idea is you've made the bins very, very small. These probability density functions are sometimes called density distribution. And it's a function that allows us to calculate probabilities. And in particular, the probability a random variable has a value between A and B is equal to the area under the density curve between A and B. For example, here we have a histogram. You can see there's this, if we wanted to calculate the probability that people are between 180 and a height of 185, we would need the area under the blue curve plus the area under the green curve, because that's the area under the curve between 180 and 185. We'll be doing a lot more work with these probability distributions in our next chapter, but for now, that's it for this video. Thank you for watching.